Hello everyone, my name is Ankit. Today we are going to completely deconstruct the calculation of electric field at all the points of a conducting and non-conducting sphere for both solid and both solid and hollow. We are not just going to remember or memorize the formulas or end results. We are also going to see from the first principles what is a solid conducting sphere or a conducting sphere, and what separates it from non-conducting sphere. And we are going to do it with both solid and non-solid. Sorry, for both conducting and non-conducting spheres. Keep it in mind. What we are going to do, we are going to see the formulas for both the cases, that is conducting and non-conducting spheres. Even though it may seems like there are conducting spheres, and in conducting spheres there will be two cases of solid and hollow, and in the same case for non-conducting sphere there will be two cases of solid and hollow. But what you will see, the formula for conducting sphere for both solid and hollow, and non-conducting sphere and non-conducting spheres hollow, will come out to be exactly the same. And how we are going to do this, so let's just jump to the code. So first of all, what I said ki, what's the difference between a conducting sphere or non-conducting sphere. So if I have a say sphere which I am calling it to be a conducting sphere, and I have a sphere which I am calling it to be a non-conducting sphere, what the difference between both of them will be is ki, we know that there is a, if the name suggests it's conducting sphere, what it means that ki it's a conductor. That means it's made up of a metal. So the basic principle of a conductor is ki when you put a charge inside a conductor, say any conductor, if you put a charge inside a conductor, either solid or hollow, even if it is a solid, say it's a solid conductor, it's a solid conductor. That means if it is a solid conductor, it will have material in its volume. And if it is a non-solid conductor, that means if it is a hollow conductor, if it is a hollow conductor, it will have material on its surface. That means it's inside, that means volume will be empty. Okay, so if it is a solid or a non-solid, that means if it is a solid or a hollow conductor, doesn't change a thing. That means ki if you put a charge, on it, it will spread, in the sense ki it's inside its electric field has to be zero. That means it will go towards the surface. That means the charges will jump to the surface. Okay, first we have to understand the basic difference between all the cases of solid, hollow of conducting sphere, and in the same sense solid and hollow of non-conducting sphere. So conducting sphere, that means it's made of a metal, a conductor. And what happens when you put a charge inside a metal, the charge will go towards the surface. And the formula we know, it will be directly inversely proportional to 1 by r, where r is the local radius of the curvature. Okay, like if any conductor, like of any shape, I am just taking a random shape and I am saying that this is made up of a conducting material, what will happen ki if you put a charge inside the conductor, the charges will go towards the surface. And the formula which is saying that sigma is inversely proportional to r, it's simply saying ki the value of surface charge density at any point will depend upon the local radius of curvature. That means if I draw a simple radius r, the value of sigma will be directly proportional or inversely proportional to it. That means if I have this point, this will be having more charges, or you can just say the point at this will have more surface charge density than the point at this, guided by this formula. That means simply saying ki since this is a conductor, it will allow movement of charges. There, if we put any charge in any case, that is conducting sphere having a solid mass wala, or if it is a hollow conducting sphere, in both the cases what you will see, the charges will spread evenly on the surface. Now, what's the difference between a conducting sphere and non-conducting sphere? So, if it is a non-conducting sphere, you can just imagine it that the charges, if you put, like if I put a charge here, okay, that charge will be staying there. Okay, it's not going to, I can say it's not going to spread. That means charge will at this sit at this place only. That means there won't be any free movement of charges, and be it solid solid non-conducting sphere or be it hollow non-conducting sphere. Again, what's the difference between solid and and hollow? It simply says that solid will have charges in it, material in its volume, and hollow will have material on its surface. Okay, now if we understand this, there is this case of solid and hollow conducting sphere and non-conducting sphere, we can go further with the discussion. Just one thing you have to take away from all of these discussions, that if it is a solid or non-solid conducting sphere, charges will sit at the surface. That means even if you put a charge at this point, it will induce uh, it will induce a negative charge, or you can just simply say that charges will have a free movement and they will go towards the surface. Okay, and if it is a solid or non-conducting sphere, then charges will sit at the exact position and it's not going to move. Okay, so let's start with our understanding of how we are going to deconstruct the electric field at all points, either inside on the surface or outside, for a conducting sphere or for a non-conducting sphere. So one thing you have to understand that you can see that if I have a non-conducting sphere, okay, you can see कि if there are charges inside the non-conducting sphere, be it positive or negative, it will sit at the same position. It won't be going to the surface. But if we have a conducting sphere, charges will go toward the either in the case of solid or hollow. Only in this case, like even in this case, if we have a charges spread evenly on the surface, they will keep on the surface only. That means ki they are not going to move. They will be situated there, and the value of electric field or electric field inside on the surface or outside will just be the same as in the case of conducting sphere, either solid or hollow, because you can see the charge distribution for conducting sphere, this one and this one, all three of them will be sitting at where? All three of them will be sitting at the surface. Okay, only in the case of non-conducting sphere, and only in the case of non-conducting spheres solid, we can see that charges will be inside the volume also, inside the surface also. Okay, so let's deconstruct the values ki how we are going to calculate the electric field and everything for all these. Like you can see there are four cases. If I am saying ki cases kitne hain, so there will be, like, if you count, okay sir, there is solid, hollow conducting sphere, solid and hollow non-conducting sphere. But as I have told you, since in all these cases the charge distribution is same, so obviously the value of electric field, even if you derive with any method, is going to be same. We are going to derive it using Gauss law. I hope you all know what is Gauss law. Even if you don't know, I am just going to briefly tell you what is Gauss law. But you have to understand in all these cases, like this case 1, 2, 3, let me just say 3, and this going to be 4, we are going to see since the charge distribution is same for 1, 2 and 3, the value of electric field at all the points will be similar for all these three cases. Only the value of electric field at every other point will be changing for the case of fourth one. So let's jump straight to the calculation of electric field for all these three cases in one manner. Like we are not going to calculate electric field individually for all three different cases. They are essentially the same cases. So we are just going to calculate the electric field for these three cases in one go. And we are also going to calculate the electric field's graph, like with the variation of electric field. We are also going to see via a graph. So I hope you are understanding things. Let me just tell you what is Gauss law briefly, because Gauss law is a very fundamental law, and it is very, very, very important for us to calculate electric field, because otherwise it will be a bit difficult and lengthy. Okay, you can calculate electric field using Coulomb's law also, and Coulomb's law also, using that the value of electric field can be simply equal to F by Q. But since there are variations of charge distribution, it becomes very essential that we have some methods that make our calculations very easy. And that one method is Gauss law. And I have just told you it's a very fundamental law. It depends upon electric flux, and I hope you understand what is flux. Flux is nothing but flow, movement of flow. That means if anything which is having a flow, we can call it a flux. Like if you want to know ki what is flux in essentially in your daily lives, you can like feel it ki what is flux. Like when you open your fridge, you will feel that the cold air, and if you are opening the fridge and also the freezer, you will find the flux of cold air coming from the freezer will be more than the flux of cold air coming from the fridge, the lower part of the fridge. Which means what? We can calculate the value of electric flux also, in the sense if this lines are representing flux. So if this is flux, say flux 1, and these are flux 2, so flux 1 will be lesser than the flux 2, and since we are calling it the flux of electric field, so we are just going to call this to be a electric flux. So how Gauss law uses flux and how Gauss law is connected with flux? So Gauss law simply says ki Gauss Gauss law simply says, and it's a very fundamental law of the nature. So Gauss law simply says the flux of electric field through through a closed surface or closed Gaussian surface. Okay, sometimes we imagine surface and we call that surface to be a Gaussian surface. It simply states that the electric flux of a electric flux through a closed Gaussian surface, a closed surface will always be equal to the value of, we also represent electric flux by phi, will always be equal to total charge enclosed by the surface divided by epsilon naught, which is permittivity of free space. Okay, so the value of flux according to Gauss law will be equal to pi q enclosed divided by epsilon naught. Now once we know ki what is Gauss law and once what we know what is electric flux, if you want to know ki what is electric flux and what is Gauss law in detail, I will make another video about both those things. But essentially for our purposes, these two things, that electric flux is nothing but flow of electric field. Okay, first thing. And what Gauss law says, that the value of net electric flux through a closed surface will always be equal to the total charge enclosed by that closed surface. Like if this is the surface, and we can say if there is a charge situated here, the value of electric, that is the net flux which is going out of the surface because of the charge situated inside the surface, will simply be equal to what? Will simply be equal to the total charge enclosed inside this Gaussian surface divided by epsilon. Okay, okay, let's go to our calculation of electric field. Let's go on to calculate the value of calculation of electric field. And also one thing I missed, and that is ki flux will be equal to what? Nothing but electric field multiplied by the value of surface area. Okay, and if we are saying we don't know what's the surface area, so you can just say the electric field multiplied by, if I am just calculating in terms of what is the infinitesimal amount of electric flux, that value will simply be equal to what? Integration of our electric field multiplied by the elemental surface area. Okay, we are going to use these formulas. That's why it's important to point it out ki what is the value of electric flux, what is the value of, and how is electric flux connected to electric field and the surface area, and how is the electric flux is connected also to the Gauss law. Okay, and because we are going to calculate electric field, it's important to know how Gauss law is going to be applied. How we are going to apply Gauss law? We are first going to find out the value of electric flux. Okay, how we are going to find out the value of electric flux? First we are going to assume or draw a Gaussian surface. Okay, and Gaussian surface always depend upon ki what kind of material you have, what kind of geometry you have. For a sphere, obviously Gaussian surface is going to be a sphere only. Okay, for a wire having a linear charge density lambda or anything like that, a rod, you are going to have the electric flux calculation based on Gauss law by using the Gaussian surface of a cylinder. Okay, so let's calculate. I have already told you ki one, that was 1, 2 and 3. That means what? One was solid conducting sphere, second was what? Solid, sorry, a hollow conducting sphere, and third was what? Hollow non-conducting sphere. In all these three cases, we are going to see कि charges were what? Charges were where? Charges were on the surface. And if we have charges on the surface, okay, if we have charges on the surface, that means inside this sphere, if we are considering this sphere to be of having radius r, we are going to see that inside this sphere there is no charge. Okay, so how we are going to calculate electric field, and where we are going to calculate electric field? So we, for all the cases, for 1, 2, 3 and 4 also, we are going to calculate electric field at 3 points, and also we are going to plot the graph, the variation of electric field with the distance from the point that is the center. Let's say the center is C. We are also going to plot the graph of the variation of electric field. So first, how we are, where we are going to calculate electric field? We are going to calculate electric field at 3 points, and those 3 points will be, first will be inside, second will be on the surface, on the surface, and third will be outside. And what will we do last? What will we do last? We will also plot the graph, that is the variation of electric field, that is the variation of electric field with respect to the distance from the center. Okay, let's just calculate the electric field for inside. How we are going to calculate electric field for the inside? So I already told you we are going to apply the basic principles. The first basic principle will be Gauss law. And how we apply Gauss law? The first basic thing is we are going to do what? We are going to draw a Gaussian surface. Let me just take another pen. That will be better for you to visualize. Okay, going to draw. We are going to draw a Gaussian surface. Okay, my drawing is not good, so pardon me on that. I hope you can see this is a Gaussian surface, and the radius of this Gaussian surface, we are going to say it is small r. So if it's a Gaussian surface, we are going to see how much charge is accumulated inside this. We know the formula to be equal to what? The value of flux will directly be equal to the charge enclosed divided by current. So you can see in all these three cases, we are not just talking about one, we are talking about all the three cases, that is conducting sphere, solid, hollow, and non-conducting sphere, hollow. That in all these three cases, there is no charge present inside the sphere. That means the value of Q enclosed will be 0. And if the value of Q enclosed is 0, phi E will be equal to what? 0. And if phi E equals to 0, that means E dot S, this is our definition of electric flux, will also be 0. That means inside the conducting sphere, solid, hollow, and non-conducting sphere, hollow, electric field we are always going to find to be equal. Electric field we are always going to find to be equal to 0. Okay. Now in the second case, we are going to draw, in the second case we want to know what is the electric field on the surface. That means now our value of R will be increasing from R to capital R. That means our Gaussian surface will also be equal to what? Having the same radius R as the sphere that we have had in the first place. That means here the value of capital R, which is the value of our Gaussian surface, will be equal to capital R. Okay. Now you can see the value of charge enclosed by that Gaussian surface. So how much charge we imagine that this surface had? We initially imagined that the surface is having a charge of Q. That means the value of phi enclosed that is the value of flux, will be equal to what? Q enclosed divided by epsilon naught. And since we have said ki we are taking the whole sphere side, the Gaussian surface, or we are just saying ki the value of Gaussian surface radius is equal to the sphere's radius, that means the value of charge enclosed will simply be equal to Q divided by epsilon. Okay. Now if we have the value of charge enclosed to be Q, now how we are going to calculate the value of electric field? We know that the value of electric flux will be equal to E dot ds. Okay, E dot ds, and we integrate this value. Okay, now since we know that the value of electric field will be what? Symmetrical, because it's a sphere. That means we can take this E out of the derivation, out of the integration. That means the value will be equal to what? E multiplied by the integration of ds. And what is the integration of ds? Integration of ds will just give us the value of whole surface area, because we are calculating the electric flux whole surface. The value will simply be equal to what? E dot s. Okay, where s is representing the surface area, E is representing the electric field. The value of flux, which is E dot ds, was equal to what? Value of Q divided by epsilon naught. So if we are trying to find the value of E, it will simply equal to what? Q divided by epsilon naught multiplied by what? Value of surface area. What's the value of surface area of a sphere? It simply comes out to be equal to what? 4 pi capital R square. So this is the electric field at E equals to R equals to R. Electric field inside was equal to what? Inside was equal to 0. On the surface we are getting what? Q by 4 pi epsilon naught R square. If you are comfortable with this, now let's go to the outside. So in order to calculate electric field on the outside point, we are again going to say, let's say this point is P, which is at a distance of r, and in this case the value of small r is going to be greater than the value of capital R. Okay, how we are going to again calculate the value of electric field here? Again we are again going to calculate the value of electric field using Gauss law. Means the basic principle that we have to first calculate what? The value of electric flux, and the value of electric flux will be equal to what? Total charge enclosed divided by epsilon naught. And in order to calculate the value of electric flux, we have to first we have to first draw a Gaussian surface. Where do we get the Gaussian surface? So if this is the radius r, this is the point position distance from the center r, we are just going to take the point distance, that is r, to be our radius of the Gaussian surface. That means this is going to be our Gaussian surface having radius r. Okay, and this Gaussian surface is enclosing this whole sphere. This Gaussian surface is enclosing the whole sphere. That means this Gaussian surface will have the charge to be equal to what? Q, and be divided by epsilon. Okay, now in order to calculate the value of electric field, what we are going to see? We are again going to apply the same principle, that electric flux will be equal to what? E dot ds, and that value will be equal to Q by epsilon naught. And again we are going to see that the value of electric field, since this electric field will be radially outward at all the points, it will be again coming out of the integration. That means the value will simply be equal to what? Integration of ds equals to Q divided by epsilon naught. Now this time the value of integration of ds will depend upon what surface we have chosen, and the surface we have chosen is the bigger one, that is having radius of r, and r is greater than r. That means we are going to integrate for the surface the bigger or Gaussian surface. In Gaussian surface we will have a radius of small r, so the value of sphere's total surface area will be equal to what? Total surface area will be equal to 4 pi small r square, which will be equal to Q divided by epsilon naught, or you can just say that the value of electric field will come out to be Q by 4 pi epsilon naught r square. So this is the electric field which we have derived outside, this is the electric field which we have derived inside, and this is the electric field we have derived to be at at the surface. So if we have all these three, we are just going to plot the graph. We are just going to pause, plot the graph. I hope you can like take a screenshot or anything. Okay, let's just plot the graph. We have all these three values. We have all these three values. All these three values. So let's just plot the graph for the electric field calculation at all these three values. Okay, so if this was my sphere, if this was my sphere, and these were different points, say this point was at a distance of r, this point was at a distance of capital R, or this point was at a distance of small r. What we have just seen, key for r smaller than r, electric field was 0. For r equal to r, electric field was equal to q by 4 pi epsilon naught multiplied by 1 by r square. Or you can just say ki the value of 1 by 4 pi epsilon naught is nothing but k, so q by r square. And for r greater than r, we are seeing the value of electric field outside will be equal to k q by small r square, where the value of r is greater. So if we plot the value of electric field, say this is my graph for electric field, this is my axis for electric field, okay, and this is the distance r, this is my distance r, this represents electric field. So inside point electric field will be 0, and it will be 0 from the center to the point which we are calling as surface. Okay, that means if we plot the values from the center, we are plotting these values. That means if this value of r equals to capital R, electric field inside from the center, that is 0 to r equals to r, will be 0. From the center, it's just going to start from the center, sorry, from the surface, it's just going to start from having a value of kq by r square. And after, if we are going to approach, after if we are going to go away from the surface and we have r greater than r, like this point, we are going to see that the value of electric field is directly proportional to what? Directly proportional to 1 by r square, because we are going to say ki k is a constant, we already know the value. Charge we have taken, we are not going to change, that means that is also a constant. That means the value of electric field will just be inversely proportional to the square of r, and we know the graph of square of r will go like this. Okay, so this is going to be the variation of electric field with respect to distance for all the three things, for all the three, that means solid, conducting, solid, hollow, and non-conducting, hollow. Okay, we don't have to do it separately for all three. We can just say if the charge distribution is same, the all three points, that is inside, on the surface, and outside, will carry the same electric field, and also carry the variation of same electric field represented by this graph here. Okay, okay, I hope you have understood everything. I will also make a video on Gauss law and applications of Gauss law. Also, briefly explain to you ki what is electric flux and everything. So don't worry about that. It's a very interesting concept. But if you have the basic understanding of first principles, you are always going to go through with it, and you don't have to remember anything. You will understand these things. Okay, you will understand how the physics of these basic principles work. And once you understand physics, once you understand what is happening, it's just simply like opening the door of the fridge. It's so simple, it's so simple when you see things. Okay, and seeing things only come from the understanding of principles, and everything works on the understanding of basic principles. From falling of this, if I leave this pen, from falling of this pen, okay, from falling of this pen to throwing a rocket into the orbit of Mars, which Elon Musk is hoping to do. Okay, so let's go on to calculate electric field let's go on to calculate electric field for non-conducting solid sphere. Okay, we have done it for all these three cases. Only the case remaining will be non-conducting solid sphere. So let's see. We are again going to calculate for all these 3 points: inside, surface, and outside. Even in this case, you are going to be very very amazed कि the three cases that we are talking, inside, on the surface, and outside, two cases will have the same exact variation of electric field, will have the same value of electric field as we have derived for the past three cases. Can you guess which case will have different variation of electric field? Think about it while I draw my very bad drawing. Okay, so it's the case of non-conducting solid. Okay, non-conducting solid. Solid means what? Shit. Sorry. Solid means what? Solid means the value of material. The materials will have the material will be situated in the volume, not only on the surface, but volume will carry some material. Like there is a ball, okay, like anything you have seen obviously what is a solid and what is a hollow thing. So a ball, okay, like the ball which we play cricket with, it's hollow inside, okay, but why, okay, you can say ki, um, that that balls we see, ball bearings we see, okay, those things are what? Those things are solid. So we are saying that this non-conducting sphere which we have, it's solid in nature. That means there will be charges in its volume. Charges where it will be in its volume, or you can just simply draw it like this also. The whole sphere will have material inside it. That means obviously if we are saying that this material is carrying some charge, that means charge will be carried inside the whole volume. And since the conducting nature, yeah, non-conducting nature it has, that means whatever charge a particular material have, it will have it at the same place. It will not be moving, because non-conducting spheres will not allow free movement of charges. So if we are saying the charges are situated into whole of the sphere, that means if I take a small sphere, it's the center here. If we are going to take a small sphere, we are going to take a small sphere also. Inside the whole sphere, it's also going to contain some charges. And the value of total charge inside this small sphere, say if I am saying that this is having a radius r and the whole sphere is having a radius of capital R, will not going to be same. What is going to be same is that the value of charge density is going to be same. What I mean by that, what I am saying is if the whole sphere is having a charge q, and this small sphere, because we are in small sphere of small radius r, will have a small charge q, what we are going to see is, since the whole sphere is symmetric or have uniformly distributed charge, the value of charge density is not going to change. That means the value of charge divided by volume in both the cases is going to be same. Okay, even if it was a very 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 small sphere, that means I am saying very small, infinitesimally small, having a small radius ekdam dr or something like that, very small radius r, it also has some sort of charge which we can say to be infinitely small dq, and having a small volume you can say dv. That means if I have the charge density same, which means the value of total charge for the whole sphere divided by the volume of the whole sphere, or this sphere which is I am considering of having radius r, will have the value of charge small q divided by volume small v. Okay, or if I am saying even it's a infinitesimally small sphere, the value of charge that it will carry and the value of volume that it will carry, the ratio is going to be same for all the three. Okay, So from this you can just calculate ki what will be the value. So value will simply be equal to what? If I am just saying ki what will be the value of Q in terms of rho, you can just say ki the charge sphere, the small charge sphere that we have. Let's take this out. The small charge sphere that we have, this value will be equal to total charge. Sorry, this value will be equal to charge density multiplied by small volume V. Okay. So let's calculate using this basic mathematics. Okay, ki what should be the value of electric field inside the sphere? That is the sphere which is having small r radius. So what we are going to do? Ki understand, we have understood this. We have to calculate electric field inside, right? Let's say ki we are trying to calculate electric field inside, and at inside any point which is smaller than radius r. That means if this was the radius capital R, if this was the radius capital R, we are saying ki we are trying to calculate electric field at this point P, which is having a small radius of R. What we are going to do? We are just going to simply draw our Gaussian surface. Okay, let me just draw it with a different color so that you don't confuse it. So we are going to draw a Gaussian surface taking this point's distance as our radius. And again we are going to apply our basic principle of Gauss law. And what Gauss law says is the total flux will be equal to what? It will simply be equal to net charge enclosed divided by epsilon naught. And we have done the basic mathematics. The charge that will be enclosed inside it will simply be equal to what? Small charge Q will be equal to charge density multiplied by the small volume of this sphere. So if we are trying to calculate the value of electric flux, which is E dot nothing small ds, and integration of this equals to charge enclosed, which will be Q divided by Q divided by epsilon naught. Okay, and if we are trying to calculate the values, okay, let me just do it here. If we are trying to calculate the value, you can see the electric field again is going to be symmetric, and it will be symmetrically coming out of the integration. That means E dot ds will be equal to charge Q divided by epsilon naught. The value of ds will depend upon this Gaussian surface, and that Gaussian surface will have a value of ds to be E dot 4 pi, since the radius is small r, 4 pi r square equals to the value of total charge Q, and we can even substitute the value of total charge Q with the charge density. So the value will be charge density rho multiplied by the value of volume, small volume V, divided by epsilon naught. So the value of electric field at inside point will be coming out to be what? Charge density, small charge density, charge density rho, volume V. What is the value of volume V? Since the Gaussian sphere is having a radius of r, we can say simply that the value of Gaussian sphere's volume will be equal to what? 4 by 3 pi small r ka cube divided by what is the value of surface area? We have just calculated to be 4 pi r square. Can you see ki what things are getting cancelled? This 4 is cancelled, this pi is cancelled, this r square is cancelling the r cube. That means only thing remaining will be r. So the value of electric field at inside point will simply be coming out to what? Rho r by 3 epsilon naught, because the 3, which is 4 by 3, 1 by 3, it will be coming towards the denominator. So this will be the value of electric field, which will be rho r by 3 epsilon naught, which will be for a non-conducting solid sphere. Okay, this is the only thing which will be different. Other than that, if we are going to calculate the electric field, say at the point which is on the surface, which is having a radius, a radial distance of r equals to r, what we are going to see that the value of electric field on surface will come out to be equal to what? Again we are going to apply the same principles, that we are going to have a Gaussian surface which is having the radius of r, which will be equal to what? R equals to r, and again if we have having the value of r equals to r, again we are going to calculate the value of flux. And since this Gaussian surface will encompass all the material inside the sphere that was having the charge of q, that means the value of q enclosed will simply come out to be what? Q divided by epsilon naught. And again the value of flux, you can say ki if E is symmetrical, the value of ds will only be integrated, value will be equal to q by epsilon naught. That means this integration of ds will give us the value of the surface area of the Gaussian sphere, which is having the radius to be equal to r. That means simply the value of electric field at r equals to r will simply come out to be what? Q divided by 4 pi epsilon naught r square. Okay, and similarly if we have a point P which is having the distance of r which is greater than r, again on the outside point r greater than r, we are again going to apply the same basic principle, which is we are going to see if we are having the Gaussian surface, if we are having the Gaussian surface, we are having the Gaussian surface having radius of r, it will also have the whole sphere which is carrying the charge inside its surface. That means the total charge inside the Gaussian surface having radius r greater than capital R will have the total charge of q, and again the value of q will be divided by epsilon naught will be equal to E dot the value of integration of ds, and this time the integration of ds will give us the value of total surface area of the Gaussian surface which is having a radius greater than r, capital R. So it will again simply come out to be equal to what? E q by 4 pi epsilon naught multiplied small r square. So this is the value of electric field which is outside. This is the value of electric field which is on the surface, and this is the value of electric field on the inside. If we are trying to calculate, if we are trying to put it into a graph, we can just simply see what will be the value, how will the electric field variation take place. Okay, we are just going to see what will be the variation by plotting the graph. So if this was my sphere, non-conducting sphere, and this was my radius r, we are again going to plot it from the center. So if this was my electric field, this is my y-axis carrying the electric field, and this is my x-axis which is carrying the separation, that is the distance r. So if we move from center, that means if we move from r equals to 0 to any point, okay, to any point, that means r still being less than r. That means if this is the point which is r, this is the point which is saying ki r equals to r. So from center, that is 0 to r equal to r, we know ki electric field inside will be equal to what? It will be equal to rho r by 3 epsilon naught. Electric field on the surface will be equal to what? It will simply equal to k q by r square, where k was nothing but 1 by 4 pi epsilon naught, and again outside point, that means E out will simply be equal to what? K q by small r square. Here r will be equal to r, and here r will be greater than r. So essentially, if we are just plotting the variation, we can simply say ki in this point, that means between 0 to r equal to r, the value of electric field inside is directly proportional to r, because charge density is going to be constant, 3 is a number, and epsilon naught is also constant. That means electric field will be linearly increasing. And what is the linear graph? Yeah, linear slope. It will simply be increasing like this. Okay, and it will be stopping at this point. At this point, the value of electric field will be equal to what? K q by r square, which is also proven by this. If you are thinking, ki, sir, how will we get this value from this value? So you don't have to do anything. Just write the value of charge density. Charge density will be equal to what? Q by V. And since the value of R at this point will be equal to what? Rho will be equal to what? Charge density by volume, which will be 4 by 3 pi r cube, right? Multiplied by multiplied by charge density by volume multiplied by R divided by 3 epsilon naught. That means 3 and 3 will be cancelled out. Um, 3 and 3 will be cancelled out. And since R will be equal to R, you can just replace it by this. Then R will be cancelling out R cube, which will be R square. And the value will simply be equal to what? Q by 4 pi epsilon naught R square, which is nothing but this value only, but just we have put this in terms of K and we have put this in terms of 1 by 4 pi epsilon. Okay. What will be the variation of electric field outside? That means from R to, let's say, infinity. What will happen? Electric field outside will be directly, yeah, inversely proportional to R square. That means it will having the graph of something like this. Okay. So to summarize this all, I am just going to point it out. Key this part that is on the surface and outside is same. If you don't remember it, I'm just plotting the graph for the graph for all three, yeah, for 1, 2 and 3. The graph was what? Graph was something like this was the electric field, this was the radius. Electric field inside, that means from 0 to R equals to R, was not having any value. That you can also represent it by a different color. You can say the value of electric field inside was 0. Only after it reaches R equals to R, it jumps to electric field having a value of KQ by R square, and after that it's jumping, yeah, it's decreasing by a factor of 1 by R square. Okay, so this thing, that means 1 by R square के inversely proportional होना is same for the last case, that is non-conducting solid sphere, and all the three cases. If you don't remember, I am just going to point out what three cases were. 1 and 2 were representing conducting sphere. One was representing solid or hollow. You can just see whichever you want to say. So it was solid, it was hollow, okay, conducting sphere, and this was what? This was non-conducting hollow. So all three will be having this variation. Only this one will be having this variation, and even in that, till even in that, after the R equal to R value, that means when you put the value of electric field from the, when you look from of the value of electric field from the surface towards infinity, it will be same. Only the value of electric field inside will be directly proportional to R. That means it will linearly increase, reach the value of KQ by R square, and again decrease in this manner as all the three cases were decreasing. So I hope you have understood the basic funda on how to solve all this. See, you can memorize everything. Okay, I am not going to say you should not do, but everything, once you have understood, once you can clearly see, it becomes very easy, and that understanding will only come when you understand the basic principles. And for that also, if you are not getting the very idea, sir, what is Gauss law, how to approach problems with Gauss law, because I am just starting with the application of Gauss law. This is one of the applications of Gauss. So if you still don't understand what is Gauss law and how to apply it, we are going to make another video in which we are going to explain what is Gauss law and how to handle problems of Gauss law, and also some questions are asked based on electric flux. Okay, so we are also going to look upon the basic questions on electric flux. We are going to put our work, our basic understanding to test through those questions, those principles. So I hope you understood this. I hope you have taken a good look at it, and bye.